we are going to start is a reduction of the prochiral carbonyl compound. And for all this reduction, we are going to use the borane derivatives. Now, what is this borane? Borane is BH3. Suppose if I have the prochiral carbonyl compound like this, if I allow this to react with BH3, everyone knows that the reaction, this reduction will take place according to the anti-Markovnikov's rule. And here, since this is prochiral, when the reaction will take place or the alcohol which are formed, they are going to give us the racemic product. Because जो प्रोटॉन BH3 अटैक करेगा यहाँ पे, तो BH3 अटैक कहीं से भी कर सकता है. इफ यू रिमेंबर हमने पढ़ा था रिडक्शन में हमने क्या पढ़ा था? BH3 is very small reagent, so it can attack from the top phase or as well as it can attack from the bottom phase. तो यहाँ पे कैसे भी अटैक हो सकता है. And as a result of which this OH may be cis to the methyl group or it may be trans to the methyl group. So this is my trans product and this is my cis product. So I'm going to end up with a racemic product since the reagent which I have used is achiral. तुम्हारा starting material है prochiral, but this is achiral. That's why I'm going to end up with the racemic product because both way attack is possible. But rather than using simple borane, we can use chiral borane reagents for these reactions. Okay, and we are going to study the different chiral borane reagent for this particular reaction. And out of that, the first reagent that we are going to talk is the Midland reagent. This Midland reagent is being developed by the Midland, starting from the, this is also called as alkene borane. You can see this structure. This is called as alkene borane. इसको बनाने के लिए the reaction has been started with, you can see this is 1,5 cyclooctadiene and its reaction with a simple borane. So when this reaction will take place, we are going to end up, this is called as 9-bora bicyclo 331 nonane and shortly called as 9-BBN. This 9-BBN, it is on reaction with alpha pinene. Okay, अब यहाँ पे ये reaction पहले तो कैसे हुआ ये समझा. ये तुम्हारा बोरेन है, एक्चुअली ये तुम्हारा डाइबोरेन टाइप है जो डाइमेरिक फॉर्म में होता है. बोरेन हमेशा डाइमेरिक फॉर्म में ही होता है. So this will give you the double bond. This across the ring यहाँ पे add हुआ, double bond का reduction हुआ, and we are getting this borane complex. Now this borane complex on the reaction with alpha pinene. यहाँ पे catalyst का stereochemistry is totally decided by this alpha pinene. Right now you can see alpha pinene पे ये जो 1 position पे proton है, which is having the R configuration, and 5th position the bridgehead are your chiral. So they are having certain configuration. अगर मैंने SS use किया तो मुझे stereochemistry अलग मिलेगा. अभी फिलहाल मैंने क्या use किया है? RR. The configuration at the 1 and 5th carbon is RR configuration. And that is going to decide the stereochemistry of this catalyst, how it is going to react. That is completely decided by this alpha pinene. अब alpha pinene में देखोगे यहाँ पे double bond है. अब ये double bond को reduce करेगा ये borane. Borane in यहाँ से कहा जाएगा, ये अगर तुम देखोगे यहाँ पे तो this is my first carbon, this is my second carbon and this is my third carbon. So boron जो है वो third carbon पे गया है और प्रोटॉन यहाँ पे गया है. तुम्हारे बोरेन एडिशन जो होता है हमेशा एंटी मार्कोनिकोव्स रूल फॉलो करता है. इट इज गोइंग टू द थर्ड कार्बन. सेकेंड कार्बन इज मोर सब्स्टिट्यूटेड. It is going to the carbon which is less substituted. So here it is going to the third carbon and proton is added over here. तो अब यहाँ पे तुम्हारे पास ये जो reagent है alpene borane, this is your chiral trialkyl borane. It is not boron hydride. अगर तुम देखोगे यहाँ पे इसके पास अभी हाइड्रोजन नहीं है. पहला वाला हाइड्रोजन यहाँ पे यूटिलाइज हो गया, एक हाइड्रोजन इस यहाँ को यहाँ पे दिया और एक हाइड्रोजन यहाँ पे दिया. B2H6 में से इसके अगर मोनोमेरिक फॉर्म में लिखोगे तो ये क्या बन गया? BH3. I'll just take the pen. Wait. See this particular boron, this B2H6. यहां से हमें क्या चाहिए? सिर्फ BH3. ओके अब यहाँ पे क्या हो रहा है? एक कॉम्प्लेक्स फॉर्म हो रहा है. बोरॉन एक कॉम्प्लेक्स ऐसे बना रहा है. यू कैन सी दिस. तो अब यहाँ पे बोरॉन जो है it has formed 2 valency, तो यहाँ पे सिर्फ क्या बचेगा, एक प्रोटॉन. Remaining 2 protons are given here, and that's why we are getting this bicyclo compound, this one. Now this boron is left with only 1 proton, so that is again undergoing the reduction process, जहाँ पे proton इसको मिलेगा और इसको मिलेगा boron. Now I can see this particular boron is not having any hydrogen. So this particular reagent or a catalyst which we are going to use in the reaction, that is not a boron hydride, it is a trialkyl borane. Okay, तो जब reduction होगा तो reduction के लिए proton तो चाहिए ना, तो proton कहाँ से मिलेगा, that you remember. इसमें बहुत important step है, ये याद रखना. The source of hydride ion, whenever the reaction will take place, the source of hydride ion is the proton which is attached at the second carbon. ये जो second carbon पे ये जो proton है, this is comparatively more acidic and that is going to take part in the reduction process. ये तुम्हारा boron hydride नहीं है, ये तुम्हारा trialkyl borane है. And here the source of hydride is the proton which is attached at the second carbon. इसके ऊपर भी क्वेश्चन आ सकता है. ये टर्शरी प्रोटॉन है तुम्हारा, and this is tertiary proton which is more acidic in this reaction, and that is going to give us the reduction reaction. Okay, अब ये example देखो. यहाँ पे हमने क्या किया, हमने लिया है deuteriobenzaldehyde. This deuteriobenzaldehyde we have allowed it to react with alipene borane. Alipene borane is your this reagent. हमने ये reducing agent use किया, and now the attack will take place from the top phase or the bottom phase. It is completely decided by the stereochemistry of this alipene borane. So here it is allowing, you can see, it is allowing the borane from the bottom phase, and therefore the proton attack is taking place from the top phase, and I'm going to end up with the S-benzyl alcohol 100% enantiomeric selectivity. हमें क्या मिला है, S alcohol selectively मिला है, because the asymmetric induction is completely decided by our chiral reagent. So this is your asymmetric synthesis which is controlled by your chiral reagent. Okay, now why we are getting only S alcohol as the major product, that we are going to start. So now here there are two things. See, this is transition state 1 and this is transition state 2. मैंने क्या किया, यहाँ पे सिंपली तुम्हारा एलिपीन बोरेन ड्रॉ किया है. यहाँ पे अगर ये स्ट्रक्चर देखोगे पूरा, ये एलिपीन बोरेन है. दिस इज ऑल्सो एलिपीन बोरेन विच इज सेम. दोनों का स्टीरियोकेमिस्ट्री मैंने एज इट इज रखा है. बट नाउ रिगार्डिंग दिस, you can see, you can imagine when the attack will take place, your phenyl group that may be above the plane and your deuterium will be below the plane. You can imagine this also. Here deuterium is above the plane and phenyl group below the plane. So there are two-way attack possible. Either ये approach ऐसे होगा या approach ऐसे होगा. अब दोनों में से कौन सा approach easily possible है, that you understand. यहाँ पे अगर तुम देखोगे, there is interaction between this CH3 group and deuterium. But when this attack will take place, there is interaction between the phenyl group and methyl group. Where is more steric crowding? Transition state 1 or transition state 2? Transition state 2, where it is very difficult. Here the crowding is more. And as a result of which, selectively, this alipene borane will approach the carbonyl through this particular complex where the deuterium and methyl will come in the interaction. And as a result of which deuterium will be below the plane and phenyl will be above the plane. And therefore, after hydrolysis, I'm going to end up with the S alcohol with 100% enantiomeric excess. So generally we say when we are using the alipene borane, the RE phase is recognized and we are getting formation of S alcohol as the major product. Okay, इसके पूरे transition state में how your ligand is approaching, sorry, this is not ligand, this is reagent, how your reagent is approaching your carbonyl group, that will decide the stereochemistry of the reaction. Okay, यहाँ पे Midland catalyst जो है वो बहुत selective है. It is used for aliphatic or allylic or aromatic aldehyde and ketone. So you can reduce them selectively using this Midland reagent. Okay, concept क्या था, वापस समझो. We are doing reduction of prochiral carbonyl compounds, and here we are using the borane reagents. If I'm using the borane reagents over here, we need to remember the borane reagents. If you use the simple achiral reagent, you will always end up with the racemic product. But अगर इसके जगह पे ऐसा कोई chiral reagent use करते हो, तो selectively we are going to get only one of the isomer. यहाँ पे हमने एक catalyst पढ़ा, that is your Midland reagent, and Midland reagent is giving us selectively S alcohol that we have studied. Okay, I hope this first example is clear to everyone. एक reagent मैंने पढ़ाया, that is your Midland reagent. Okay, I'm going to talk about one more catalyst. This is called a CBS catalyst. We can use this CBS catalyst also for the reduction of the prochiral ketone or aldehyde. The CBS is being prepared by the three scientists, Kore, Bakshi, and Shibata. And from their name, it is being designed. The name of the catalyst has been designed. That is CBS catalyst. Now the CBS catalyst is of two types. You can say this is prolinol. This is diphenyl prolinol. यहाँ पे अगर सिर्फ प्रोटॉन होते तो इसको प्रोलिनॉल बोलते हैं. यहाँ पे diphenyl group है, so this is diphenyl prolinol. Either you can start with R isomer or you can start with S isomer. तुम्हें इसको enantioselective बनाना है. और एक चीज यहाँ पे in this, यहाँ पे हमने alpine borane बनाया, but what we started with this plus alpha pinene. What was that plus alpha pinene? Which was 1R and 5R. Suppose instead of this alpha pinene, if I take S alpha pinene, 1S and 5S alpha pinene, तो मुझे ये minus isomer मिलेगा, and the reagent which I will prepare, that will be exactly opposite. So what product you will expect in this reaction? अगर मैंने उसका दूसरा reagent use किया, instead of this 1R and 5R, if I use 1S and 5S, what is the product expected here? You will get R benzyl with the 100% enantiomeric excess. तो यहाँ पे तुम कौन सा ligand use कर रहे हो, reagent use करे. ये reagent बनाने के लिए हमने ये जो ligand use किया अल्फा पाइनिन, उसके स्टीरियोकेमिस्ट्री ने डिसाइड किया कि कौन सा प्रोडक्ट फॉर्म हो गया. तो अगर इसका स्टीरियोकेमिस्ट्री अपोजिट कर दिया तो ये प्रोडक्ट जो बनेगा वो भी अपोजिट ही बनेगा. Okay, so similarly you can see here the R or S, there are two type of the isomers that you can use, but any selectively only one reagent you will use. Either you will use the R isomer or you will use the S isomer. Now here it is being allowed to react with this BH3, a simple BH3. BH3 generally जो packing मिलता है, you get it, it is complexed with some solvents, aprotic solvents. So here THF, tetrahydrofuran. So you will get always this BH3 complex with the THF. So when this reaction will take place, see here there will be a reaction. Okay, यहाँ पे नाइट्रोजन के साथ बोरॉन का एक बॉन्ड बनेगा और एक ऑक्सीजन के पास बनेगा. So there will be a reaction over here and I will get this CBS BH catalyst. But इसके जगह पे if I use any alkyl derivative of the borane, though I will get the methyl boron catalyst. So CBS catalyst is of two types, either CBS BH catalyst, that is hydride donor, or you can use CBS methyl catalyst, which is your alkyl borane. So there are two type of borane. One is alkyl borane and one is the hydride borane. So any one of this you can use it for the reaction. Okay, I hope the preparation is clear. You can start from R or S diphenyl. दोनों में से कोई भी एक लेना है. So accordingly you will get your chiral reagent for the reaction. ये जितने भी हम पढ़ रहे हैं अभी reaction, ये तुम्हारे chiral reagent control है. So when this reaction will take place, suppose if you are using this, अब तुम देखो यहाँ पे ये catalyst use किया है, but reaction के लिए हमने use किया है BH3. Why? Because if you look at this particular boron, is it capable of donating any proton? It is not capable of doing the reduction of this. Okay, it is not capable of doing reduction of this. Previously when we have used this alpine borane, what I told you, though this is alkyl borane, but there is a proton at the second carbon here. This particular proton is capable of donation. तो ये वाला जो था ये प्रोटॉन डोनेट होता है. तो रिएक्शन जब हमने किया, हमने कोई भी दूसरा BH3 यूज नहीं किया, हमने डायरेक्टली इसको यूज किया बिकॉज इट इज हैविंग दिस एसिडिक प्रोटॉन विच इज कैपेबल ऑफ डूइंग द रिडक्शन. तो प्रोटॉन रिएक्शन में से इस रिएजेंट में से ही मिला, इसलिए हमने उसको रिएजेंट बोला. बट यहाँ पे अगर तुम देखोगे, इट इज नॉट हैविंग एनी प्रोटॉन टू डोनेट, and that's why for the reduction the proton which is required, we are going to take it from the BH3. So this BH3 will now do the reduction in presence of this, and that is going to give me the enantiomeric excess. So this is which type of asymmetric synthesis? Control. Here the catalyst will decide whether the attack will take place from the top side or bottom side, because somewhere क्या होगा, ये जो BH3 है तुम्हारा, जो तुम रिएजेंट करके यूज कर रहे हो, ये जो BH3 है, somewhere it will be complexed with this nitrogen, and that will decide whether the reactivity will take place from the top side or bottom side. So the stereochemistry of this catalyst will decide the attack. So here if you see the larger group, generally the phenyls are taken, and the smaller groups are methyl or ethyl. You can see more selectivity is observed when you are using more bulkier groups. So up to 96.7% enantiomeric excess is being observed in this particular reaction using this oxazoborolidine catalyst, which is also called as CBS catalyst. Now in the CBS catalyst, exactly how it happens, I told you just now. ये जो तुम्हारा catalyst है, it is going to interact with your BH3. And you can see it is being forming a complex with the BH3, a tetra, that quaternary salt it is forming. And therefore, when this BH3 is approaching this ligand, approaching the reactant, whether it will approach from the top side or bottom side, it is completely decided by this particular factor. So here you can see the attack is taking place over here. How it is taking place? यहाँ पे दो अप्रोच हो सकते हैं. देखो, एक अप्रोच मैंने यहाँ पे ड्रॉ किया है. एक अप्रोच कैसे ड्रॉ किया मैंने? The RS side is nearby to this catalyst and L, the larger group is away. तुम ऐसे भी ड्रॉ कर सकते हो ना, C double bond O, RL is near and this is RS is away. But इसमें क्या होगा? When the RL will be nearby, there will be repulsion between this methyl group and RL. And therefore we are expecting the attack will take place from the side of the smaller group, and hence when it will take place from the side of smaller group, I will end up with specifically one product जिसको hydrolyze करके हमें मिलेगा एक alcohol. Okay, opposite way भी कर सकते हो. कैसे करोगे opposite way में? Suppose मुझे ये जो alcohol मिला जिसमें smaller alcohol above the plane है, larger group जो है वो below the plane है, and smaller group जो है वो above the plane है. Here the stereochemistry is decided by your catalyst, right? So if you want the opposite stereochemistry, change the stereochemistry of the catalyst. Because तुम क्या बोल रहे हो, ये कौन सा asymmetric synthesis है? This is asymmetric synthesis using chiral catalyst. So if I want opposite configuration in the product, change the configuration of the catalyst. जो तुम्हारा reagent है, जैसे तुम्हें अल्फा इपॉक्साइड बीटा इपॉक्साइड, जो इपॉक्साइड चाहिए था उसके हिसाब से तुमने DT चेंज किया, राइट? तो जो काइरलिटी इंड्यूस कर रहा है उसका कॉन्फ़िगरेशन चेंज करो. जैसे उसका कॉन्फ़िगरेशन चेंज हो गया, प्रोडक्ट का कॉन्फ़िगरेशन विल बी डिफरेंट. दिस alpine borane is giving me the formation of S alcohol. अगर मुझे R alcohol चाहिए तो क्या करोगे? किसका कॉन्फ़िगरेशन चेंज करोगे? alpine borane, alpha pinene which was used. हमने कौन सा यूज किया था? 1R 5R. इसकी जगह पे यूज करो 1S 5S. जैसे ये चेंज हो गया, यहाँ पे मुझे R प्रोडक्ट मिलेगा 100% enantiomeric excess. So whosoever is introducing the chirality, change that configuration to get the opposite. But every time this is not possible. Okay? जैसे अगर तुम देखोगे इस केस में इजी है R प्रोलिनोर और S प्रोलिनोर, बट DT जो है टार्टरिक एसिड दोनों इजीली अवेलेबल नहीं है नेचर में. तुम्हारा L प्लस टार्ट्रिक एसिड है वो इजीली अवेलेबल है, तो अगर L प्लस अवेलेबल है तो वो उसका कॉस्ट कम है, D प्लस का कॉस्ट ज्यादा है, तो हमेशा दो आइसोमर्स जो होते हैं दे आर नॉट इक्वली अवेलेबल इन नेचर, so one may be costly and one may be cheaper, and therefore we generally use any specific one type of catalyst. If both are equally available in nature and both have the equal cost, wo jo stereochemistry hoga, that will be completely different. You can say that reaction will have more weightage because with the help of both the catalysts you can prepare both the type of the configuration. तो ऐसे रिएक्शन का डिमांड ज्यादा है. So this was the mechanism why we are getting this particular alcohol as a major product in the reaction. Have everyone understood this part? Any doubt in this? तो हमने क्या पढ़ा? Prochiral carbonyl, how to do the reduction of that. We can reduce it using two borane reagent. Either we can use the Midland reagent, which is directly a reagent for the reaction, or we can use a CBS catalyst, which is complexed with the borane, and that is going to give us the reaction. And दोनों के हमने mechanism part भी देखे. Next part that we are going to start is the reduction of prochiral alkene. We are going to do the reduction of alkene, but this time which kind of alkene we have taken? We have taken prochiral alkene. Now for the reduction, again we have different reagents. You can use normal reagents like ranitidine or platinum or palladium, lithium aluminum hydride, or sodium NaBH4. We can use those kind of reagents, but if you use those kind of reagent, you're going to use, or you're going to end up with racemic product. To get the anisotropically pure compound, these kind of reagents, you can see, you can use the reagent, but on the screen right now, whatever reagents you can see, these are all achiral boron hydrides. So apart from the regular reducing agent, you can use this boron hydrides also. But all these boron hydrides are going to give me the racemic reaction. For example, if you can see this is your Z prochiral alkene. When this is undergoing the reaction, you can see in this reaction, when the reduction will occur at this particular carbon. See, this is your boron catalyst, right? Borane reagents, and borane reagent, if you remember, this is called as the reduction hydroboration oxidation method. Hydroboration oxidation में क्या होता है? पहले there is addition of this boron across the double bond, right, according to the anti-Markovnikov's rule, followed by the hydrolysis in presence of NaOH and H2O2, that gives you corresponding alcohol. Generally, we get the primary alcohol in the reaction because the reaction take place according to anti-Markovnikov's rule. So now you can see in this case, since we are using a chiral borane reagent, there are two type of products which can be formed. And since I'm getting two different products, when the hydrolysis will take place, I'm going to get the R and the S butanol in 50-50%. So I'm ending up with the racemic product. But now to get the enantiomerically pure compound, there are two type of reagents that we are going to study. The first is IPC twice BH, which is called as diisopinocamphanyl borane. And second one is IPC BH2, which is monoisopinocamphanyl borane. यहाँ पे देखोगे तो this is your isopinocamphanyl derivative. ये कितने हैं? Twice. That's why it's called as diisopinocamphanyl borane. और यहाँ पे वो एक ही है, इसलिए उसको बोलते हैं monoisopinocamphanyl derivative. Okay. So now we're going to study these two reagents for the reaction, the same reaction which we studied where we were getting the racemic compound. So let us start with the first. This is IPC twice BH. You can see here our starting material is alpha pinene, which we have used it for the preparation of the Midland's reagent also. Okay. So this is your enantiomerically, this IPC2 twice BH, it's your enantiomerically pure compound. And that is obtained by the reaction of alpha pinene with this B2H6. B2H6 is nothing but the diborane form of BH3. And then this reaction take place around in 3 days to get the syn hydroboration. You can see here this particular BH3. You can see this is BH3. If you do remember in Midland reagent how we carried out the reaction, we added proton to this and then we added boron to this, right? The same thing is happening here. You can see here this double bond has become single bond. You can see, check this. This double bond has become single bond and the boron is added. Similarly, there is one more molecule which is consumed of alpha pinene, and there also we can see this double bond has become single bond. So this is syn addition. On the same site, the addition take place. And this syn addition is going to give me the formation of 2-distereomeric trialkyl borane. This is distereomeric trialkyl borane, which is obtained during the reaction. And further, its oxidation will give us the, if you carry out this reaction with the prochiral alkene, and they are going to give us the formation of synalkene. How they will, that will come across the mechanistic part. Right now you can see यहाँ पे मैंने अलग अलग वे प्रेजेंट किया है. सबसे पहले this ring, if you see this particular ring, this is 6-membered ring. So I have written this 6-membered ring in a simple planar form like this, and this is also one of the way of presenting the IPC twice BH reagent. अब यही इसी मॉलिक्यूल को हमने और एक वे में चेंज किया. हमने क्या किया, ये जो साइक्लोहेक्सिन रिंग था इसको प्रॉपर चेयर फॉर्म में डिजाइन कर लिया. So if you are doing this is on chair form, you can see since it is added on the same site, you can see here this particular BH3, it is at equatorial position, and यहाँ पे अगर तुम देखोगे तो यहाँ पे भी equatorial position पे है, तो ये भी above the plane है. So it is on the same side of the rings, and you can see this reagent. अब इसको हमने smaller way में draw करने के लिए क्या किया है, this is my BH3 and this is the next carbon which is attached to the BH3. Now this next carbon is attached to, you can say, 3 functional group. एक तो boron है ही. Apart from that, it's 3 other valency. 3 other valency कौन है? एक proton है, एक दूसरा carbon है which is attached to this CH3, and this is CH2. So amongst these 3, we have decided which one is smaller, which one is larger, and which one is our medium size. तो अगर तुम देखोगे तो ये smaller group है, ये larger group है, and this is your medium size ring, right? So these 3 groups we have presented here. So you can see this is my carbon which is attached here, attached to one smaller group. There is larger group here, and in the front we have a medium group. Similarly, you can see this is the other carbon which is attached to one large group on this side, medium group on this side, and this is my smaller, that is the proton. Okay, तो इसको यहाँ पे ऐसे प्रेजेंट किया है. तो जब हम मैकेनिस्टिक एस्पेक्ट देखेंगे, we are not going to draw this complete ring, rather we are going to present like this. Okay, so this is my another carbon. This is forming one cyclohexane ring, and this is forming another cyclohexane ring. Okay, and this is my boron reagent. So we have presented this in the simple way in order to present the mechanism. Now what happens during the reaction, that you understand. We have taken the same Z prochiral alkene, and rather than taking a chiral borane reagent, we have taken chiral boron hydride. Previously, when we have used the achiral boron reagent, if you remember, we were getting 50-50% of this. But right now you can see when this reduction is happening, I'm going to get one of the compound in the more amount, one of the isomer in the more amount. And which alcohol I'm getting? I'm getting R-butanol in 93.5%, and another compound that is S-butanol in 6.5%. Okay, so here this particular boron reagent is completely controlling the approach, whether it will take place from the front side or it will take place from the back side. Okay, यहाँ पे अगर तुम देखोगे तो ये Z है, Z मतलब cis type of alkene. तो ये cis type of alkene, you can see either these 2 methyl groups can be on the left side or they can be on the right side, and accordingly you will get the 2 different products. Now why we are getting, okay, I have presented this also. अगर मैंने see Z प्रोकाइरल अल्कीन के जगह पे अगर मैंने ई अल्कोहल ई आइसोमर लिया, उसका ट्रांस आइसोमर लिया, तो व्हाट इज हैपनिंग? The trans isomer, you can see this methyl group on left side and this is on right side, or you can imagine this is on right side and this is on left side. So two different approaches are there, and we are going to end up with the compound. But you can see here, though we are using a chiral boron hydride, but we don't have a selectivity here. This is almost like the racemic mixture. अच्छा, by the way, ये enantiomeric excess calculate कैसे करते हैं? R isomer percentage minus S isomer percentage. And previous case अगर तुम देखोगे तो R का percentage कितना था? 93.5 and the S was 6.5. So if you'll subtract it from there, you will get the R isomer 87%. It is enantiomeric excess, and here we are getting 13%, right? So if you'll see this IPC twice BH, this particular alkene is giving you the, this particular reagent is giving you the higher enantiomer selectivity for the cis alkene rather than the trans alkene. Okay, now let us understand why this happens, why it is selective for the cis alkene to give the higher enantiomer selectivity, and also we will understand why we are getting the R-butanol as a major product, not the S-butanol. This is completely the stereochemistry which is controlled by your reagent. Now what exactly happens, understand. Okay, do you remember this? I told you just now, I explain you how to present the chiral catalyst. This is your chiral catalyst. These are the groups attached to it, and these are the groups attached to this carbon. This is boron, which is having the proton here. Now when alkene is going to approach, there are two-way approach possible. While approaching, maybe the protons are towards the catalyst, towards the reagent, and methyls are away from the approach. Or you can imagine this case where the two methyl groups are towards the reagent and the protons are away from the catalyst. Okay, this is going to form interaction, a coordination hoga, that will form a cyclic transition state like this. Okay, now you tell me whether the transition state 1 is feasible or transition state 2 is feasible. You can say, if you'll see the particular case, ये वाला देखो, यहाँ पे तो ये large वाला चलेगा. देखो यहाँ, in this case you can see this large group is away from the plane. Okay, and this proton is coming towards the plane. So it is kind of like यहाँ पे interaction है, but इतना ज़्यादा नहीं है because they are not in same plane first of all. But there is interaction between this medium size group and this proton. You can see in transition state 1, this medium group is coming in the steric interaction with this proton, whereas in the transition state 2, this medium size group is coming in interaction with the methyl group. And this is having more steric interaction or steric crowding, as a result of which this approach is very difficult. And when this approach is difficult, you can see this is away from the plane and BH3 is approaching from here. So it is, you imagine, ye H hai, right now what you can see, H is towards you and methyl is away from you. Now just imagine you're observing from this side. I'm standing here. Okay, if I'm standing here, I'm looking towards this side. The proton is on my right side or it is on my left side? Right side. And the methyl group is on my left side. So you can see here, okay, proton is on my right side and methyl is on my left side. And boron is approaching from the bottom in the plane. So you can see the boron is approaching in the plane. Similarly, imagine you're standing here and you're looking at the molecule. So now methyl group is on my right side and the proton is on my left side and boron is approaching here. So when this will happen, I'm going to end up with the R-butanol. And when this will happen, the hydroboration oxidation, that will give me the S-butanol. Of course, we can see the transition state 1 is more feasible. It is having the less crowding. Therefore, we are going to end up with the R-butanol as the major product during this reaction. We have studied for which isomer? Z isomer. Z isomer of the alkene. Okay. Now let us understand what happens. We are having trans alkene. Then here there are two approach possible. You can see here At this position, medium size group is coming in interaction with proton, whereas medium size group is coming in interaction with methyl group. So there are two ways possible. Either this proton will be towards this, or this methyl is away, or we can say methyl is towards this and proton is away. This is your trans alkene only, but it can also approach the reagent in two different ways. So now in this two approach, again imagine you're standing here, you're looking at the molecule, methyl group is on my right side, proton is on my left side. So methyl on right side, proton is on my right side, and the boron is approaching in the plane. Now for the backside carbon, ये मिथाइल का और ये मिथाइल का कॉन्फ़िगरेशन क्या है? ट्रांस. So draw it in opposite way. Previous reaction, this methyl and this methyl should be on same side because we were having Z configuration. Now here it should have the trans configuration. Okay, similarly for this also, imagine standing here, proton is on my right side, methyl right side and proton on left side. Okay, now tell me, यहाँ पे क्या हुआ? यहाँ पे अलग अलग अप्रोच क्यों नहीं पॉसिबल हुआ? यहाँ पे परसेंटेज इतना डिफर क्यों नहीं किया? प्रीवियस केस में यहाँ पे सिलेक्टिवली मुझे एक आइसोमर मिल रहा था, और वो भी कितना? 93.5% एक आइसोमर, एंड दूसरा कितना? सिर्फ 6.5. But in this case, I'm getting 56.5 and 43.5, almost nearby to resting. If we look at this particular transition state 1, this transition state 1 of Z isomer, okay, medium size group and your large size group, both of them are coming in interaction with the proton. So this is having the highest stability. You can see this approach. This is having a less steric repulsion. And because of that reason, I'm getting this R isomer with the higher percentage. But now you can see over here, this methyl medium size group and large size group, both are coming in interaction with the methyl group. So this particular isomer or this particular transition state, if you'll see, that is having the highest steric repulsion ever. इसलिए percentage कितना है? सिर्फ 6.5, और इसका सबसे ज्यादा है. But if you look at this, here one group is coming in interaction with proton, while other group is coming in interaction with large, that is methyl group. यहाँ पे भी same है. यहाँ पे larger group जो है, that is coming in interaction with the proton, while the medium size ring is coming in interaction with methyl. Okay, so that means what? One is having proton interaction and one is having methyl interaction. Previous case, this was having both proton interaction and this was having both methyl interaction. तो ये सबसे stable है और ये सबसे unstable है. But in this case, you can see there is one proton and one methyl interaction. तो अगर तुम देखोगे तो ऑलमोस्ट दोनों के अप्रोच सेम है, तो मुझे एग्जैक्ट परसेंटेज मिलना चाहिए था 50-50, बट आई एम नॉट गेटिंग 50-50. I'm not getting 50-50. I'm getting 56.5 and I'm getting 43.5. That means 13% enantiomeric excess I'm getting. Why I'm getting that 13% enantiomeric excess? अगर दोनों में same kind of interaction है तो ये ज्यादा क्यों मिला? Here the medium and proton, they are both are above the plane, so they are more closer. Over here the large group and methyl group, though we are saying they are having interaction, but this is below the plane and this is above the plane. Over here again you can see the medium size group and this methyl group, they are in same plane. Now here there is more repulsion compared to this, and because of this reason again we say the transition state 1 is more favored and we are getting this. But to some extent, as I told you, both are having similar interaction. Only the thing, to smaller extent, the transition state 1 here is preferred compared to the second one. तो यहाँ पे enantiomeric excess तो मिला, but कितना मिला? सिर्फ 13%. That means my reagent is not capable of creating the enantiomeric pure compound for the trans isomer, trans alkene. But it can definitely create a better enantioselectivity in case of cis alkene. So this particular reagent that we have used, that is IPC twice BH, we can use this for reduction of prochiral alkene, which are having the cis isomer. Now my question is, suppose ये जो reaction है, this let's say Z isomer, ये जो reaction है, यहाँ पे मुझे क्या मिला? R isomer as a major product, right? If I want S isomer as a major product, what changes you will do it in this reaction to get the opposite isomer as a major product? Reagent is chiral. This reaction is controlled by the reagent, right? So if you need to change the configuration of your product, change the chirality of your reagent. So we started with, for making this IPC twice BH, we started with 1R 5R alpha pinene. So if I take, instead of 1R 5R alpha pinene, if I take 1S 5S alpha pinene, then I will end up with S butanol as the major product. Okay, हाँ, यहाँ पे भी अगर मैंने 1S 5S वाला IPC twice BH बनाया तो भी याद रखो, because it's the same type of reagent, only the thing तुमने क्या किया, उसका chirality change किया है. Therefore that reagent also, it's active towards cis alkene more rather than trans alkene, क्योंकि approach तो reagent का same ही होगा. And that's why again it will show you the more reactivity towards the cis alkene, or sorry, the better results for the cis alkene rather than trans alkene. Only the thing, amount जो है वो change होंगे. R will be minor and S will be major. That is the change that is going to happen if I'm going to change the configuration. Each of this question is of 5 marks. Each question. If they ask you to write a note on prochiral, that is reduction of prochiral alkenes, IPC twice BH is of 5 marks. Sorry, it's of 2.5 mark. And one more reagent that is we are going to study, that is of 2.5 mark. Okay, clear everyone? So let us start with the next one. This is also IPC, that is isopino-camphenyl reagent, but this is mono. That means यहाँ पे हमने सिर्फ एक सिंगल ये यूज किया है, ओके, और यहाँ पे सिंपल BH3 यूज करके इस डबल बॉन्ड का रिडक्शन. So we have started with again 1R 5R alpha pinene, and here the reduction is going to take place, and that is going to give me this reagent, which is further on reaction with BH3. This is something like after reduction, this is my boron complex, and this remaining part, that is your triethylamine. Again, they are in complex form. So if you allow it to more react with more BH3, thus this particular BH3 will now form a complex with triethylamine, and this will leave, and I will only left with this reagent. That is called as your IPC BH2. Now you have BH2, 2 protons over here. Okay, previous case में क्या हुआ था, ये proton use करके भी यहाँ पे एक alpha pinene join हुआ था. That's why we call it as IPC twice BH. Now this is IPC BH2. Okay, my question is, what is the difference between this and Midland reagent? 9 BBN, that is your cyclooctadiene reagent that way you get it. So यहाँ पे वो attached होता है. तो ये तीनों भी नियर बाय ही है सारे reagents, but selectivity सबका अलग अलग है. Okay, now this reaction, you can see we have started with the reduction of Z cis alkenes. I'm getting 61% of R butanol and 39% of S butanol. So of course I'm getting how many enantiomeric excess? 22% of enantiomeric excess, that is of R. अब ये वापस R क्यों मिला? Because हमने alpha pinene जो select किया था, alpha pinene which we have used is 1R 5R. So again I'm ending up with the R butanol. हाँ, but it is not compulsory कि R ही देता है और S ही देता है. It's completely depends on the stereochemistry and what is your transition state. It may happen if your catalyst configuration is S, you may end up with a product which is R. Okay, so there is no correlation between the configuration of the catalyst and the configuration of the product. हाँ, for the specific catalyst it is fixed. अगर मैंने ये वाला use किया तो definitely I will get the R-butanol. तब तुम relation बोल सकते हैं, but this is related to the catalyst. It's not a generalized statement. Okay, so now I'm getting the R isomer. So can you observe one thing over here? Z is giving me only 22% of enantiomeric excess. Instead of this, if I take E, now you can see this 86% of R-butanol and 14% of S-butanol, which is giving me around 72% of enantiomeric excess. That is indicating the monoisophenol camphenyl borane. This particular reagent is selective or giving higher enantio selectivity for trans alkene rather than giving for the cis alkene. This time we are getting less enantiomeric excess for the cis alkene and we are getting more enantiomeric excess for the trans alkene. Okay, तो ये जो मैंने reagent select किया यहाँ पे तो it is giving you the different product. I'm getting the for the better enantiomeric selectivity for the E isomers. Now why this happens, that you understand. Here you can see this is your reagent which is drawn in the chair form. और यहाँ पे अगर तुम देखोगे तो ये boron है, smaller group, this is hydrogen present here. This is larger group here and this is your medium size group. Okay, दोनों साइड पे मैंने जो स्ट्रक्चर है वो सेम ड्रॉ किया है. यहाँ पे हाइड्रोजन है, larger group, and this is medium size ring. So we have drawn in both the transition state the same type of the configuration for your catalyst. Now this reagent, sorry, the reactant, other reactant. Now this another reactant you can see, this we have taken, this is your E isomer, trans isomer. So while taking this trans isomer, you can take this in such a way that you can see here, this particular methyl group, it's towards the alkene and these two are away from it. Okay, here these two methyl and proton are away and these are towards. There are two different approaches we have shown. Now you can see here transition state number 1 and transition state number 2. दोनों को compare करो and find it out which is suitable and which is not and why. Percentage wise तो दिख ही रहा है कि transition state 1 is preferred, but why is it so? This is medium group which is above the plane and this is proton which is above the plane. So now they have interaction. Okay, but यहाँ पे अगर तुम देखोगे तो medium size group and this particular methyl group, they have more steric clash over here. At the same time, you can see this is larger group. This is your larger group. This larger group, you can see this is going to experience, this methyl is there and this proton is there, but they are away from the plane. Here also, this methyl is, this is also proton and this is also methyl. Again, the same kind of steric interaction, but they are away from the plane. So they are not going to make any difference for this larger group. But over here, the medium size ring, that is going to experience a lot of clash. And that will decide whether the R or S will form as a major product. Okay, so here R is formed 86% and S is formed 14%. Right? I have not shown the other thing. You can try it. अगर होगा reaction, suppose let's say Z का होगा, तो कैसे होगा? Imagine करो. कैसे imagine करोगे? Either we can imagine this, let's say, two methyl groups on the same side, and I can imagine these two protons are away from the plane, right? Or I can imagine, sorry, these protons towards the catalyst and methyl groups are away from the plane, right? This is, let's say, my transition state number 1, and this is my transition state number 2. Which is again preferred? 1, because over there the medium group will have interaction with the proton. Imagine करो ये वाला अल्कीन यहाँ पे प्रेजेंट है, तो ये CH3 हो जाएगा और ये H हो जाएगा, तो यहाँ पे ये अप्रोच इजीली पॉसिबल है, सेम टाइप है. बट यहाँ पे अगर तुम देखोगे, अगेन द सेम टाइप ऑफ अप्रोच, H here, CH3 here. हाँ, यहाँ पे हमने क्या देखा, दिस Z isomer and E isomer. Now in this case I told you कि imagine this particular E isomer is giving us the difference, but suppose instead of this if I have Z isomer, तो Z isomer में if the methyl groups are towards the catalyst, that will be the better approach compared to the away, and as a result of which I will end up with the R on S isomer, but this time the difference will not be much. The difference in the two transition state will not be much, and as a result of which I don't get the enantiomer selectivity in the case of Z isomer, but we get the better enantiomer selectivity for the E isomer. So in short, we have studied two reagents. One is IPC twice BH and one is IPC BH2. Okay, if I make these reagents with 1R 5R alpha pinene, we get, now this is for specifically for these reagent, they give you R configuration as the major alcohol. This reagent is more selective for the cis alkene. तो cis alkene के लिए अगर तुम्हें cis alkene का reduction करना है and you want to cis alkene to be converted into alcohols, and if you want one of the major product and minor product, then definitely use IPC twice BH as a reagent. But suppose if you want to make it for the trans alkene, then specifically use IPC BH2, because IPC twice BH gives you higher selectivity for cis alkene and IPC BH2 gives you the higher selectivity for the trans alkene.